One more interesting property about the dual is the relation between cycles and cutsets. So you might have got the feeling from exercises and previous discussions that cycles and cutsets seem to relate to each other in a certain way or another. And indeed, if G is a connected plane graph, then a set of edges in G form a cycle if and only if the corresponding edges in G star form a cutset. So let's look at an example. So if we have this graph G, and then we form G star, so we do this. And then one cutset is, for example, the edges of this triangle. One cycle is this triangle. And indeed, because of this edge crossing property, intuitively it seems that since our cycle encircles this vertex, or if we take the four edges that are around here, we encircle two vertices. Encircling means we cut off. If the edges of G are knives, then they would cut off the edges of G star, and so the corresponding edges of G star would be a cutset. So that looks nice, but let's see how to prove this precisely. So take a set of edges in G. First, let's prove that if this set forms a cycle, then the corresponding edges in G star forms a cutset. So if it forms a cycle, any cycle encloses a bunch of faces of G. So it encloses a set of vertices of G star. Why is the set of vertices non-empty? Well, because by construction of G star, we're going to have one vertex in each face of G. So since we're enclosing at least one face of G, we're enclosing at least one vertex of G star. Also, we're not enclosing all vertices of G star, just a proper subset. There will be some vertices outside because we have the infinite face at the very least outside. These vertices are connected by edges inside our cycle. Why is that? Well, if they were not, if we have our cycle, if we have these two vertices inside our C and they are not connected, this means that the corresponding faces of G do not have any edge in common. They might be somehow different. And then this cycle, so-called cycle C of ours, would circle both faces twice and would somehow have to come back to the same vertex multiple times. So it cannot be a cycle. So by its being a cycle, we cannot have this situation, and the situation we must have is that we have faces that share an edge. For that reason, our vertices will be connected. All that to say that this cycle of ours in G will have a connected component of vertices of G star inside it and one outside it for the same reason. So it splits G star into components. It cuts as a knife G star into components, meaning that the edges of G star that cross our cycle, that correspond to our cycle, removing them will disconnect G star into components. That is precisely what it means to be a cutset. Namely, it separates in exactly two components because it's a minimal disconnecting set. Okay, that proves that if we have a cycle in G, then our corresponding edges in G star form a cutset. Conversely, we're proving an if and only if statement, so we have to show that if G is such that the corresponding edges form a cutset, then C is a cycle. So if this is the case, well, if the corresponding edges form a cutset, it means that removing them will separate the vertices of G star in two components. So this means that C encloses a connected component of G star. But this means that C, because vertices of G star correspond to faces of G, this means that C encloses a set of faces in G. And these faces have to be connected in the sense that they touch each other. So they must look like this. And not like this with some space, with some other stuff between them. Because otherwise, removing this so-called cut set would split G in more than two components. So this cannot happen. And therefore, this face is connected. And because of that, encircling these faces being connected to each other in this sense, meaning that you can find a chain of adjacencies between them, says that it is a cycle. So in anything that encloses faces that touch upon each other successively is a cycle. This proof was a bit technical, and some parts, I admit, I was appealing more to geometric intuition. Everything can be made more precise and more slowly. If you would like, you can and should do that, but this gives you the general idea in fairly precise terms, justifying every step either geometrically or by reference to some earlier result. So in dual graphs, cycles of my original graph correspond to cut sets of my dual graph. So what do cut sets of my original graph correspond to? Well, the answer is they correspond to cycles of my dual graph. So the theorem now is the same as the previous theorem, except I have swapped the words cut set and cycles. So a set of edges in G forms a cut set if and only if the corresponding edges in G star form a cycle. Why is that? The proof is shorter than the previous proof and relies on it. So we can apply the previous theorem to G star. So it says that a cycles in G star correspond to cut sets in G star star, right? The previous theorem says that cycles in G, any graph G, correspond to cut sets in its dual. So if my original graph is already a dual, the cut sets will be in the dual dual. But the dual dual, G star star, we've already seen is isomorphic to G. So this means that really I am looking at G. So in this way, duality helped me shorten this proof. And the summary of the previous two theorems is that cut sets and cycles are dual phenomena to each other.